All right, let's finish up this section of notes with example 9. E to the pi I plus 1 equals 0. This is known as Eulers Identity, named after Leonard Euler. If you see it like on the World Wide Web, you probably see it as e to the I pi plus 1 equals 0. I stylistically prefer it as pi I, so I always write it like that. But they're the same. Multiplication is commutative. So, yes, this is I as in the imaginary unit. So this is kind of a mystical equation. First of all, it's an identity, which means it's true. It's true for all values, right? It's a true statement. That's cool. It also has all of the arithmetic operations that we learn. We have addition, right, which is really the same as subtraction, right? They're in the same category. We have multiplication up here in the exponent. That's the same as division, same priority. And then we have exponentiation. So that's pretty cool. It has all three of those things going for it. It also has the identity element of addition, which is 0. Anything plus 0 is itself. That kind of forms the basis for plus and minus mathematics. It has the identity element of multiplication, 1, which kind of forms the basis for multiplication arithmetic. It has I, the imaginary unit. That's the square root of -1. Pretty cool. It has pi, which is the probably most famous irrational number in the whole wide world. It's the geometric transcendental irrational number. And then, of course, it has E in it, which is the analysis transcendental number, 2.718. So it has the two most famous irrational numbers in the whole wide world. So that in itself is pretty awesome. But if you just scratch the surface a little bit, because you kind of notice what's missing, right? It has E in it, which is related to logs. But what's missing? There's no trig in it, is there? There's no trig. What are the two basic trig functions that compose the genetic DNA of all the other trig functions? Sine and cosine. It's missing sine and cosine. That's the only thing that I wish it had. But you know what? If you scratch the surface, it actually has sine and cosine in it. So it is bizarrely awesome. So some people actually use this equation as an intelligent design argument for the existence of an intelligent designer, right? They call that the teleological argument for the existence of a God, right? This equation is too sophisticated and complex to have just existed on its own. Therefore, it must have some intelligent creator, right? Just like the wristwatch on my arm did not just fall into this assembly of configuration of electronic parts and come to existence on its own, right? It actually was made by Casio, okay? Casio made this, okay? Same thing here. This had to have some intelligent designer. And it wasn't Leonard Euler. Leonard Euler didn't invent this equation. He merely discovered it. It was there to be discovered. Like Lord Carnarvon discovered King Tut, not calculus. All right. Like Kekulé discovered the configuration of the calculus. Benzing ring. Telephone. All right, Tyler. Who discovered the telephone? Alexander Graham Bell gets credit, but there's a backstory. There's another guy that supposedly, yeah. Anyway. Okay, Nostradamus. All right, so here's what we're going to do. We're going to kind of prove that this is true. We're not discovering it to be true, but we'll kind of see why it's true, and you'll see the sine and cosine part manifest, all right? Pretty cool. So what we're going to start with for this is, on the left-hand side, we'll start with the e to the x power series. Sound good? All right. So this is one we memorized. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial plus x to the 6th over 6 factorial. And that's about as long as the twin parade was, so I'll stop about right there. Okay. Hey, the good news is the fewer people that were in the parade meant there was more people to watch it. Yeah, okay, right? Like when you throw the ball up and you miss 3 times, you don't say that you're a sucky batter. You say you're an awesome pitcher. Okay. So, here we go. Now what do we do? Well, I am going to replace x with ix. ix. Okay? Where I is the imaginary unit. Now, in order to do that, we need to review powers of i's. We know that I is the imaginary unit. It's equal to I, which technically is the square root of negative 1. What is I squared? Negative 1, okay? I cubed, if you multiply both sides by I, you get negative I. And then I to the 4th is back to positive 1. And then the cycle repeats, okay? I to the 5th is equal to I, so on and so forth. So we say that this is congruent mod 4, modulo 4. It's modular arithmetic. So I to the 5th would be equal to I to the 6th would be equivalent to I to the 2nd, which is equal to negative 1, so on and so forth. And you can even work backwards. What is I to the 0th power going to equal to? Yeah, if you work backwards, it should equal to 1, right? Anything to the 0 power is 1. And then let's do I to the negative 1st, which is 1 over I. That should be equal to what? If you work backwards, it should be equal to negative I. And the way that you would prove that, there's actually an algebraic way to do that. All you got to do is multiply by a clever form of 1 called I over I. And you get I over I squared, which is negative I. So there's a whole neat little arithmetic that goes with powers of I. Okay? Speaking of eyes, my eyes still hurt today. Right? I don't know if it's these glasses, but whatever. Still feels like someone's pinching them. But anyway, doesn't matter. Doesn't matter. All right, I forgot where I was. Oh, powers of I. Yeah, okay, cool. Any questions on this? Little mini lesson, little review. Okay, so now what I'm going to do is go through and I'm going to replace every x with ix. So we get 1 plus ix plus, I'll just keep it kind of real here, ix squared, quantity over 2 factorial, plus ix cubed, all over 3 factorial, plus ix to the 4th over 4 factorial, plus ix to the 5th. And I'm going out kind of far on purpose, not to make a slam on the participants in the parade, but, you know, just you'll see why later. We'd see the pattern after the first 3 terms. But I'll go a little further. Okay, so that process will continue on down the line. Notice I'm not worried about the nth term here. It's not a big deal. Okay, so now what we're going to do is simplify. So e to the ix is equal to 1 plus ix. Okay, I got that. And now we'll simplify. What is I squared equal to? Negative 1. So this becomes negative x squared over 2 factorial. What is I cubed equal to? Negative I. So that becomes negative I times x cubed over 3 factorial. And then the next term, what's out of the 4th? 1. So the i's go away, and we're just left with plus x to the 4th over 4 factorial. We'll keep going here. What is I to the 5th? It's the same. You just subtract 4 from the exponent. It's the same as I to the 1st. So it's plus I to the 1st times x to the 5th over 5 factorial. And then what is I to the 6th? Well, that's congruent with I to the 2nd, right? Subtract 4 from the exponent. And I squared is negative 1. So the I goes away, but the term becomes negative x to the 6th over 6 factorial. And then that process would continue, okay? So we're just simplifying the powers of I. We're bringing them out front and changing the sign as necessary. All right, so now what we could do is we can kind of take inventory. It looks like every other term has an I in it, and then every other term in between those does not. So let's go ahead and regroup this alternating series, alternating power series, and group all the I terms together and group all the non-I terms together, right? Now, if I do that and I group all the I terms together, then those infinitely many I terms would have I in common, right? So let's go ahead and just factor that out. I'm gonna do that second though. Let's write all the ones that don't have I in it first. So I got 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus yada yada yada. So those are the terms that don't have I in them. And then I got to pick up here plus, so that'll go on forever. And now plus, all the ones that I highlighted have I, so I'm going to factor the I out, parentheses, yeah, parentheses. And now I'm left with x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus yada, 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 close parentheses. And then I'll just go ahead and say plus yada, yada, yada. There might be some other stuff out there, right? So a lot of plus yada, yada, yada for infinite series. Okay, now that I've done that, let's see if we can recognize some familiar series. This right here looks a whole lot like what? It looks a whole lot like cosine. Is it cosine? It is, in fact, cosine. That is perfectly cosine. So we can call this cosine of x. We can replace those infinitely many terms with cosine of x. Pretty neato. Plus I times, this looks a lot like sine of x. Let me write that up here. Cosine of x, sine of x. And it is exactly sine of x. And so this right here is what Euler came up with. Notice that we still don't have his identity proven yet, but we do have e to the ix, and we have written it in terms of sine and cosine, the building blocks of all trigonometry. So this was kind of the essence of Euler's work, but here's where it gets kind of cool. Let's go ahead now and evaluate that for a particular value of x. The domain is all real numbers for both sides. So I'm going to pick a value, I don't know, pi maybe? So let's go ahead and evaluate that. So we'll say at x equals pi, the number pi. We'll plug it in, and we get e to the I times pi, which stylistically, I like to flip that around, so I'll call that pi I, same thing, equals cosine of pi plus I sine pi, right? Not I spy pi, that'd be different, right? That would make you hungry for pi, but I sine pi. And now we'll just evaluate it even more because we know the unit circle, right? So cosine of pi is -1 plus I times sine of pi is 0. What's 0 times I? 0. So we end up with e to the pi I equals -1 plus 0, which is -1. So that looks pretty cool, but now I'm going to do one last thing, and again, it's stylistic. I'm just going to add 1 to both sides, and you end up with e to the pi I plus 1 equals 0. And there you go. You now know it's true. And so, yes, it does have everything we talked about before, but it has the genetic genotype. It has a phenotype that doesn't include sine and cosine, but its genotype contains sine and cosine, the building blocks of all trigonometry. So, there you go. I'm going to pause for a moment for you to reflect on that. Like, what part of your body would you get that tattooed on? I would like the forehead and get it backwards so that when you're driving in the car and people look in the rearview mirror like, oh, ambulance. Oh, Euler's identity, right? Right? Okay. That's beautiful. That's it. It's my favorite equation in the whole wide world that is yet to be discovered. There might be others out there, but this one's pretty beautiful because it's simplistic too. Okay? It's very, very beautiful. It's austere. All right? So any comments or questions on that? Thank you, Leonhard Euler. The most prolific single mathematician in the history of mathematics is Leonhard Euler. A guy named Paul Erdős actually published more, but he collaborated with more people. And Euler had more original publications. And I've told you the story about when Leonhard Euler was old and he began to lose eyesight in one of his eyes. They're like, oh no, the great Leonhard Euler is going blind in an eye. Now it's going to be harder for him to do more work, right? Because he's going to be straining an eye and he'll be less productive. And you know what the great Leonhard Euler said? He said, now I'll be less distracted. That's almost as great as his identity right there. Now I'll be less distracted. Like, you can see him like a chameleon with his eyeballs going separately, like, ooh, what's over there, right? More math. Ooh, okay. He was actually very, very, very productive still after he lost sight in one eye. Yes, Skylar, you had a question.
So normally -1 raised to any number is either going to be -1 or 1. But if -1 is raised to x over pi I, now it's suddenly e to the x.
-1 to the n is either -1 or 1 for integer values of n. Yeah? And now what you're saying, that -1 to the what? X over pi I? Yeah? Is it going to equal what? It's going to equal e to the x. You solve this for e to the x? Solve this for e to the x. Negative 1 to the x over pi I. Yeah. So let's see, negative 1 to the x over pi I. We know pi I is equal to the natural log of negative 1. Pi I is equal to the natural log of negative 1, which pi I then is equal to the natural log of the square root of I. Is that right? No, I squared, the square root of I squared. That would be I squared. And so what did you do? You replaced...
Well, what I did is I just reoriented the equation so that it was e to the pi I equals negative 1.
Oh, okay. Let me follow your logic here. Okay, so you're kind of playing around with his equation after the fact, which is fine. It's there to be handled. Yeah, with. So you solved it for pi I?
Or I raised both to the x power.
You exponentiated both sides. Like x to the that equals x to the that?
Or, sorry, I raised, so negative 1 would be the base, and then I raised both to the x power. So like it would be e to the pi I x equals negative 1 to the x.
Oh, okay. Oh, I see. You raised both sides to the x power like that. Okay. And then what'd you do?
I raised both to the reciprocal of pi I.
So after that, then you raise both sides to the 1 over pi i's power. 1 over pi i's power. Okay. And then what happens down here? These all multiply, so those divide out, so you get e to the x equals negative 1 to the x divided by pi I. So usually negative 1 to any integer power is either 1 or negative 1, but here negative 1 to any number x divided by pi I, an irrational number times the imaginary unit, gives you the function e to the x. Yeah, awesome. Yeah, you can play around it. You can, if you raise both sides to the 1 over x power, you get e to the negative 1 equals 1 over pi I. Yeah, kind of just another rearrangement. But yeah, it works for any value of x. So yeah. And you know, this is also equal to e, right? The limit as n goes to infinity of 1 plus 1 over n to the nth power. So, and that, of course, is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... They're all equal to each other. There you go. The words of the prophets were written on the subway walls. If Euler was a graffiti artist back in the day, this is what you'd see. Pretty cool. Awesome. So, yeah, there you go. Any other comments or questions about this? I hope you're sufficiently awed by this. A-W-E-D, right? Not like, oh. All right, we'll stop right there for this section.